The top is already there.
Yeah, that's what I expected.
Will you coffee after I start?
I believe so, right?
Perfect.
She's supposed to start now. If we believe the agenda. Okay, so you have a clicker here.
Right.
It's also a pointer. You also have a physical pointer, you know, in case Larry gets very excited.
I'll try to just see that.
All right, should we continue then? Next speaker is Mace.
All right, so thanks for the opportunity to talk about some recent work that I've been a part of. So today I'd hopefully sort of describe some of the latest calculations we've been doing in the dilute-dense CGC framework, which I'll briefly introduce, but I think in this audience it's not so necessary. And then I'll go over a recent paper with Vladi and Prithilish and Raju, where we really just tried to understand if there was a simple way to describe the multiplicity dependence on the harmonics of the LHC in this framework, and it turns out that there is, and it actually does a fairly nice job. And then I'll go into a little bit more detail about then a more numerically involved way to actually calculate things like harmonics and also multiplicity distributions in this dilute-dense CGC framework, which was the subject of this paper and also the subject of ongoing work. Okay, so this slide is probably not necessary in this audience, but just to sort of set the stage, really trying to describe particle production correlations in terms of high energy QCD in the CGC framework. And as Larry introduced that really you then started thinking about nuclei.
Actually, I'll introduce the saturation moment.
Well, I meant earlier today. Yes, of course, over time. I mean, I would not trying to go too in depth, but
this is a seven-week long program.
Yeah.
I think to refer to
yeah.
history of speakers.
Yeah, that's true. Okay, and so then really just sort of thinking about what this condensate means in terms of a nucleus is really that even though it's weakly coupled, and you're always thinking in terms of the weak coupling description, it really creates a strongly correlated system, and this really then changes how one actually should think about these instead of just say very simple classical dynamics, but also one has to also start thinking about quantum correlations as well. And so sort of the thesis of my talk will be that, and I hope to show, is that CGC really can produce flow, or whatever you'd like to call it, in line with what's been observed. So then getting a little bit, our hands a little bit dirty, just to say again what this dilute-dense CGC framework is really trying to solve classical Yang-Mills in terms of the eignal source charges for the projectile and target nucleus. And here I'll always be working as sort of a light projectile and a heavy target. Thinking into this, then one can appeal to what's called the dilute-dense regime, which is a power counting in the target color charge density versus the projectile color charge density. And so sort of I write this out as a power series then schematically to say how we would think of single inclusive distribution. And really that a leading order you can calculate analytically to order rho p squared, and then you have some more complicated function given in terms of Wilson lines, in terms of the target color charge density, and one can calculate that perturbatively, so on and on. Okay, what's really known though is just this leading order framework, and it's been very powerful. We'll hear talks later this week. That this isn't only used for say soft physics, which is what I'll be talking about, but also things like Marconia and photons. Then, in principle, if one takes this to all orders in this power expansion, that one retrieves what's called the dense situation, which is all orders in rho p. And so this is really then just numerically solving classical Yang-Mills for arbitrary rows, and this then leads to this IP-Glasma model, which everyone's heard of. And then it's important to point out in this dilute-dense framework, there's been a lot of work by people, or by a lot of the people in the audience, on then understanding quantum correlations like Bose enhancement and HBT correlations, in this type of framework. Okay, so if one wants, one can calculate the leading order in this single inclusive distribution. However, then if one wants to compute something like V3, so an odd azimuthal harmonic, to consider then the double inclusive distribution in terms of Fourier expansion, one can very quickly see those that you need terms that are odd under momentum reflection of one of the particles, that this must be really non-vanishing in order to get something non-zero for V3. At lowest order in this dilute-dense CGC power counting, you actually can show, and it's just shown by Larry and Vladdy, and then further elaborated with Yuri, that really one at this leading order does not get, or this is truly a vanishing contribution, and one must then look maybe to the next order, because we know that to all orders in the dense regime, it has been actually shown numerically that one can certainly get a V3. So there must be some place where some additional scattering or that actually then starts to generate this V3 from this strictly dilute dense picture. Okay, so then going forward, so as I was saying, that this was really then resolved fairly recently, in understanding that one actually needs just an additional scattering, or it's a single extra contribution in the scattering of gluon from the projectile on the target nucleus. This is what's shown here. And so then what one actually gets then, you can write down compactly for the single inclusive distribution for the even and odd components in terms of projectile color charge densities. Again, so I'm really thinking in this dilute dense regime, and I can count then the number of projectile color charge densities, and then the all orders contribution from the target. And so just what I want to sort of pick out here is then the scaling one observed. So one sees that this even contribution goes like rho projectile squared, where the odd contribution actually then comes in like rho projectile cubed. Okay, and just to say that this is in one gauge, but the same results have been obtained in a different gauge. And then in order to actually define a multi-particle distribution, one can take these single particle distributions and take products of n of these, for instance. And then with averaging over the projectile color charge densities and target color charge densities, the ensembles of these, one can then actually get a n particle distribution. So then this is sort of then how we're thinking about approaching this problem. Now, as I said, so at the even harmonics are really this lowest order, the strict lowest order dilute dense result. One can calculate even harmonics on an event by event basis. You can see that this is non-zero. However, for odd harmonics, the lowest order contribution will vanish under with the averaging. So one needs to take into account this first saturation correction, or it's at least part of the first saturation correction. The full result still remains elusive. To actually get to the full be a rho to the sixth contribution. However, as I pointed out, so this even piece goes like rho projectile squared, and the odd piece goes like rho projectile cubed. And so if one considers just a rescaling by some constant here for this rho projectile, this omega that I defined previously, which is just it's really just a valence sort, or like your valence source is being rotated by your valence source is being rotated by the target in color space. Then this omega variable also scales with C. But then what one can see very clearly then, just in terms of the single inclusive distribution that I write here, for a given single event in rows, that this really scales at leading order like rows, or like C squared. Then if I want to look at something like a Fourier harmonic, here I write this in somewhat compact notation, but the important point is that this is really what one calculates for a single event in the CGC framework. And then one has to take an average over the rows to actually get then sort of this, to get a sort of meaningful expression in terms of Vn. But writing out then this actual contribution of what this sort of the kernel for the harmonic would be, really you're evaluating a Fourier moment of a distribution over just the expectation value of this distribution. And so with this scaling that I've introduced, one can see that actually for an even harmonic, which would contribute to this Q2, you get a cancellation in this scaling variable that I've introduced. So it really does, it's factor C. And so then at least you would expect that really then there's no dependence on the momentum, or on the, on the multiplicity, whereas from the same scaling argument, for an odd harmonic, you actually then have to take into account this odd part of the single inclusive distribution, which, as I argued previously, scales like rho p cubed. So then I still actually get the factor of the scaling C. I look at the term that actually enters into this expression for the Fourier harmonic squared, and just from this simple scaling relation, I can argue then that really this term goes like the multiplicity. And so sort of a simple observation that is really then that the even harmonic should probably, or should in this dilute-dense CGC framework, really scale independently of the multiplicity, whereas an odd harmonic scales like the multiplicity to 1/2 power. Okay, so then if I then see how well this sort of scaling argument works, so what I do is I just take the scaling factor and I fix the coefficient for a single value of the multiplicity. And what I can see is for even harmonics, this is with recent Atlas data, that it does a fairly good job explaining this fairly flat behavior that's observed. And then if I take the n charge to the 1/2 power, as I argued for odd harmonics, for V3, this does a very nice job. So this, I wouldn't say it's evidence that you're seeing CGC in these collisions, but there's sort of an intuitive way, or at least a natural way to explain the multiplicity scaling that one sees at the LHC. Now, of course, there will be high projectile density effects, especially as I get to larger n charge. So, I mean, this potentially could be what one is seeing here. And then also, one should ask really how this applies then for very peripheral AA collisions, where they see that V3 is very similar, but there's a difference in V2. And so, one would ask, what should we expect for AA collisions?
You understand the lower multiplicity stuff on the even moments?
What happens here? Not so much. I don't, at least off the cuff, I don't really have a good explanation for why one doesn't see this. I mean, unless this is somehow one needs like higher order effects in rho. Okay, but so, and just to say that with doing some numerics, which this is actually extremely challenging to go to this high of multiplicities numerically, but we can do a fairly decent job, at least just qualitatively saying that it's fairly flat as a function of multiplicity.
This is classical.
So this is dilute dense. This is really, and I'll introduce this. Then sort of the rest of my talk will be spent really going into how numerics like this are done.
So this is the numerics of the formulas.
Yes, this is numerics for the, okay, so let me just get right into this then. So in order to actually, one wants to do, say, maybe a little bit more phenomenological of a calculation. And so taking these expressions we had in terms of rows for the projectile and target to calculate Gluon distribution, or single inclusive Gluon distributions for a given event, one needs to actually then sort of mock up what the initial color charge density is. And the way that we do this is really guided by IP-Glasma in the sense that we take so for a single event, we sample positions using a Glauber type of nuclear modeling. From there, one assigns then values of QS from IPSat with additional fluctuations, which have been studied by, say, Larry and Frithlish. And then this is really then for each nucleon, and this is really a position, an X-dependent variable then. So you're really describing a full lumpy nucleus for both the projectile and target. You can get this through some nuclear positioning plus IPSat. And so then there's a straightforward mapping between QS squared, saturation momentum, and then the color charge density per unit area, this G squared mu. And so here I just show 3 events with sort of this average G squared mu that you would get just from taking IPSat and some nuclear modeling. And so there's fluctuations with the given QS in each nucleon. But so this is really 3 example events from one that come from the 0 to 5% multiplicity class, or simulations. However, that's not the end of the story. So these are sort of your average color charge density one would get, but then actually one has to sample what the rows are then from, say, just assuming the MV model, which is the position dependent here. So here
How do you get to the row cubed the MV model?
well, so on average, the row cubed will be 0, of course, but
You don't. Okay. Please go ahead.
okay, that's the
No,
So-
I thought you were going to finish first. I mean, so you're producing 2 gluons.
yes.
Each gluon in production is order row cube. You're producing 2 gluons, so it's order row to the 6.
Yes.
And
then
I mean 3 from the correlation.
Right.
Yes,
And that
it's-
generates correlations.
It's only in the double inclusive distribution. For the single, as Yuri's saying, I mean, for the single inclusive distribution, on average, this row cube term would always be 0, as you can show. But yeah, so this is really only one part. So this would be like a row to the 6th contribution in the double inclusive, which would come from sort of two row cubed parts. But there should also be a row squared row 4 term, which we don't include here. Just to say.
Can I ask a nuclear
Yes.
physics question? So deuteron, so what determines the probability of for nucleon?
So this is really just this Poynton, there's this Poynton wave function which they can describe. I mean the sort of
Position.
So given the position of one nucleon, you know the radial probability for the position of the other.
I think then the function is correct there. How do you put that in the MV model?
So what I do is actually I determine QS squared for a given nuclei. So say for this proton, I determine QS squared, and this has some profile which has some width that's given from Fitz-Tehera data. But then from QS, then I map this just as with a constant proportionality to G squared mu. And from knowing then a position-dependent G squared mu, I can sample rows which are also position-dependent. Once I have my rows that are position-dependent, then I solve for the classical fields, and from there I can actually solve then, I would solve these expressions I had which were row-dependent single-inclusive distributions.
So the function is correct. It refers only to one nucleon. And then to build the helium, for instance, we have an additional distribution of the 2 nucleons.
Yes, so for the helium, the way that I would do this, I would assign each of these a QS, right? And that have some profile, and maybe they overlap or not. But from then this total helium, but as I showed here with this G squared mu, then at each space, at each transverse position, I sample a row.
Can I ask a follow-up question
Sure.
to that? So how do you take into account the fact that in the deuteron and helium-3 the nucleons are found?
Well, so that's I mean, in some sense, so the helium-3 configurations actually come from our friends in the nuclear structure community. So yeah.
I have no doubt that you can figure out where the nucleons are, but then the distribution of partons inside.
So I'm really treating these protons as just a Gaussian. So I mean, of course, like I know Bjorn for hydro has looked at actually then putting in constituent quarks and then how these are sampled, but at least for this type of calculation, it actually doesn't make any real difference if you consider constituent quarks versus just sort of a Gaussian proton. This really seems to only matter when one maps to hydrodynamic description.
Sorry.
What? I don't understand.
Well, we know that the nuclear PDFs are a bit different than the nucleon PDFs, but I suppose that deuteron and helium-3 are so light that the configuration is small enough to ignore.
You will do the same for the target.
No, but look, when you're projecting on a 2-dimensional plane, of course we have nucleons appearing to overlap on these pictures. They of course don't really overlap one to another. That's what in the end generates shadowing. So the nuclear, so if you just look at those pictures, I don't think they will give us the nuclear PDFs which are transparent. I mean, it's not going to be the nuclear PDFs twice.
It's also about how you add them, right? This is done within IT stuff, right? So what happens, you do this, essentially you take a diagram, you're adding thickness functions for each of the nucleons in the exponent, essentially. So this has, sort of nuclear effects.
So the shadowing comes out.
Yeah. Exactly. So then you from that diagram, you extract QS for the whole
nuclear.
For example, this shadowing isn't really an effect of bound nucleons being bound shadowing.
Maybe.
No nucleons overlapping.
Yeah.
Then somehow high X nuclear effects that's physics that is not included.
So sorry, quickly returning to my question, that this different configuration, is it atypical or is it typical? Because from my memory, it wasn't as elongated as was.
It's 0 to 5%.
Yeah, this is really looking at, so, okay, I mean, I'll actually show you what sort of the distribution of
Just
the,
about the pictures, the 0 to 5%.
I'm sort of-
multiplicity.
yeah, this is only for multiplicity. So, because I also have a fluctuating target, so this will, I sort of just show 3 screenshot, or like 3 examples, but these are, I can have deuteron that are separated, so the distribution, so I can show you what the distribution looks like, just getting into it. So this is actually what one has is the separation distribution that you get from taking this Huygens wave, or the probability density, and so, I mean, it's peaked at something like, 1 point something per man.
I just remember
Yeah.
proposing the wave function that it doesn't look all that elongated as everyone would like it to be, or the density of the resulting from the wave function. So I would think that, yeah, okay, so.
Yeah, I mean, there's certainly sort of, I think it's high time that there's more overlap with what's done in nuclear structure and what's done in sort of high energy nuclear collisions with respect to what information we put into these. I mean, of course, this is ignoring sort of short range correlations or.
But the wave function.
Yes, yeah, exactly. But so these are sort of okay, except the helium-3 is, it's in principle a Green's function Monte-Carlo calculation and should have a lot of physics built into it. But at least for the deuteron, this is really just a sort of simple picture. Okay, so then from these initial rows that we get from both the projectile and the target, one then calculates the part of production, which then includes these quantum effects that I previously alluded to, and really these quantum effects, that these Bose-Einstein condensation or Bose enhancement, excuse me, this is actually extremely important because you get color charge fluctuations, which will then generate things like even a proton-proton multiplicity distribution. So if I only had nucleon position fluctuations, I think it'd be very difficult to actually describe the full multiplicity distribution for PP. But with color charge fluctuations as well, and this has been previously shown using IP-Glasma as well, that really you can describe the multiplicity distribution without any extra input up to even very high multiplicities. Okay, just to say though that this also generates a negative binomial. This was known analytically for some time, but just to see again that that's really this is a genuine negative binomial distribution, convolution of negative binomials, and is not an input into our model. And really, this is how then I'll constrain all free parameters that I have. And there's of course some variability in this, but by fitting the multiplicity distribution to a known multiplicity distribution, I'll try to reduce, or I'll try to constrain all my free parameters. For what I'll show coming up, which we'll be looking at the recent STAR, the Phoenix system size scan, really the only multiplicity distribution that we have for proton, deuteron, and helium-3 gold is this STAR deuteron gold. So actually all of the free parameters I have will just be from trying to constrain this fit here. So
is this only color charge fluctuations or also additional additional QS fluctuations?
Additional QS fluctuations as well. And this will of course generate, these QS fluctations that was shown necessary, especially for this high multiplicity end, that one really needs QS fluctuations. Although it turns out, at least for the dilute dense case, for the proton-proton, that one doesn't really need much by way of QS fluctuations.
Do you use them constrained from somewhere else, or do you just?
No, I mean, so when I fix this parameter that's telling me the fluctuation of QS with respect to the mean, I mean, this I take as a completely free parameter. So, okay. I mean, I think this is the same as what you do in Plasma, right? I mean, this when you let this log of QS fluctuate. I mean, this is really sort of a free parameter for you, unless you have some way to.
Well, it's I mean, we just looked at different observables, right? So you have the PP, and then you look at also the refractive vector manipulation. So the low T behavior of that would depend on that also. So do you use 0.5 for the log?
So yeah, for the proton deuteron helium-3 that I'll show, that we use 0.5. So I mean, but
consistent with what you have there.
Yeah, so that's now, as I was saying, for proton, it turns out to actually need less fluctuation. Yeah.
Should we be worried about the high multiplicity tail?
Yeah, so of course it would be nice if we could do a little bit better here at the highest multiplicity tail. I mean, of course, these are very few and far between events, so this might just be an issue of statistics, but
Where is the 5% most central?
so 5% is most central. So if I remember, it starts somewhere like something. It's like so it ends up being something like 23, and the average end charge is something like 10. So I mean, somewhere between 2 and 3. This is where, if I remember correctly, 0 to 5 starts. So I mean, really, I'm showing this down to an extremely small. This is 1 in 10,000 or something, right? So okay, but so constraining all of our free parameters just from this fit to, or from the I'm trying to improve the agreements with the star G-gold multiplicity distribution, then we can actually calculate V2 and V3. And so here I'm showing this with some fairly fat error bars, and I'll get into this in a second. But just to say that at least qualitatively, this event-by-event dilute-dense CGC framework can do a fairly reasonable job in explaining, or at least seeing that the orders of magnitude and sort of the orderings one observes between proton, deuteron, and helium-3 can be captured in this framework. And so, as Larry pointed out, at very high multiplicities, we actually had probably overestimating high multiplicity tail. And this might be one reason why we don't do so well on V3, since we know that this is fluctuation dominated. If we have more high multiplicity events than what one would expect, that this might actually be driving V3 up a little bit. But the clear fact that we have a V2 which is similar, or a V2 for proton gold, which is smaller than deuteron, which is similar then to helium-3, this ordering, which was initially assumed to really only be a result of geometry, can actually also be explained, or at least seen qualitatively in the CGC type picture. Okay. So then, as I said, so I drew these very broad uncertainties, and this was after much pleading from some of our experimental colleagues to try to estimate our uncertainties. And I would just want to say that that there are a lot of different sources of uncertainties. So the biggest one, to me at least, is that we're really fixing all of our free parameters just by this fit to star deuteron gold multiplicity distribution. There's no reason a priori that all three of these systems, these model parameters, such as the fluctuations in QS, the average value of QS for the projectile and target, and even we have to introduce a regulator mass to actually solve classical equations. There's no reason that these should be the same for all three systems, and it's known that that these three parameters can, even in something like IP-Glasma, can dramatically change how your multiplicity distribution is shaped. And so it would be very useful, and I think also for colleagues doing hydrodynamic simulations, to have more multiplicity distributions, to really be able to then to make sort of have more data behind any theory to data comparison. Another what I think is sort of an exciting prospect, though, is really then I think this is a neat opportunity to start involving more nuclear structure into these types of calculations. For instance, things like short-range correlations, which Hen gave a nice talk about during week 5, sort of giving all the overview, but there's really been a lot of work in understanding how these work for lighter nuclei, and so going forward, it's probably very important that if, and as I'll show in the CGC type picture, we tend to believe that high multiplicity events are mostly driven by close configurations, and these are exactly the ones where these short-range correlations and other nuclear structure effects are very important. And there's a lot that's been learned or that's been sort of uncovered in the past few years that I think should be included in any analysis like this. Yes.
So, a question to that in terms of CGC power counts, right? If you're doing classical fields or such, or even the out harmonics calculation you described, let's say the two gluons come from different nucleons, not from the same nucleon, and that's usually kind of argued that, well, this is sort of a not exactly a very dilute system, right? It's still not a two nucleon nucleus, but many nucleon nucleus. So in other words, you always, at least in all the calculations we do, we neglect those any correlations between nuclei. Now, I'm not saying they don't exist. Of course, they exist and they're very important for certain questions. But so, in other words, is it consistent? So, yes, you would improve your model by including those correlations, but they're outside of the precision of the CGC part of your calculation. So, is it consistent?
Well, probably not completely consistent, of course, but I think that that's really sort of a crude way. I mean, one can sort of.
I don't think he's talking about calculating strong short-range correlations from the CGC.
No, of course.
Using input from. I mean, the CGC calculation always has some non-perturbative. Always some non-perturbative.
Yes, this would really only influence the sampling of the nucleon positions and these models. And this had been sort of done by Mark Strickman and others a while ago, where they tried to. It's really just in sort of this this blobber picture of the nucleus, which is sort of the starting point for our calculations, hydro calculations, all of this. Just the actual position of the centers of all the nucleons. Where are these located? I mean, then of course you can get into. And how to actually then treat the color fields and so what order and some classical power counting you have. But I think sort of an order zero thing is, are we getting the positions of the nucleons right? And
but
especially
once you start including target correlations, I mean, it's still folklore. You should start including Pomeroy loops as well. And I know you don't have evolution on the projector side here, so maybe it's a bit of a moot point. But in principle, you can't just put the wave function correlations in backend and forget Pomeroy loops. That would be.
I think Pomeroy loops is a very different kind of physics.
Oh, physics is very different, but power counting. You just see power counting.
Just like you're putting the Dilute-dense wave function for the deuterium.
Yeah,
so what's the difference if you also include?
Oh, that's also strictly speaking, maybe not the right thing to do. You should take the well.
Because Pomeroy was already quantified it.
because they would be of the same one.
At large X. So Pomeroy
small.
No, but this is somehow. This is the projectile. So RHIC mid rapidity. We're talking about x equals 0.01 deuteron. You really
is it only RHIC or could you look at LHC?
So I've only really looked at RHIC for what they'll show.
Well, but still, again, it's just a comment about power count.
No,
the model will get much better from.
I mean, it actually might make our model worse. I have no idea. It's just the point that at least what we see driving this effect in CGC pictures, sort of close configurations, and with this, one needs to make sure to the level of precision that we know that we're treating this correctly. And so I really think some of these nuclear wave function effects might be interesting. See what their influence is. And then finally, something which I won't touch on at all, but just to say that that fragmentation is of course a big uncertainty really in any model, but how to actually do this appropriately. That there have been some attempts, say with CGC plus Loon string model, which have done a nice job for PP data, but to really then, if one wanted to make an earnest comparison, theory to experiments, one should include fragmentation, which we do not do here. Okay, so then sort of the question is, we saw this.
Why don't you do that?
I mean, this is very computationally very challenging. I mean, the point of this calculation was really just to show that one could get this ordering, even in, say, gluons, that we're not just that it's really not as simple as some conjecture where you would expect if you have color domains that you would have proton would be.
But I just want to, I mean, this is probably not as complicated as trying to get PT distributions dependent on mass and stuff like that. It's probably just simple fragmentation of gluons, isn't it?
Well, at least sort of my understanding is that what was done here was much more sophisticated than just convoluting.
I understand,
your
but that I thought was tied in to mass ordering effects, was
yes, sort of the objective I think of this paper was really to show mass
it? This
ordering.
is probably much simpler.
You mean to just roll with the independent computation?
Yeah.
Yeah, you could do that, but then at lower PT.
Yeah,
I mean, this whole this whole thing is a question of fluctuation. So the question of when you do fragmentation, is that's a source of additional fluctuations?
Yes.
In how many hadrons you generate from per gluon.
Then you can just roll with proton.
So what you're telling me is that I shouldn't believe any of these things with gluons because fragmentation will change it all.
Yeah. I mean, but it's not among friends. I'll say that fragmentation might change things in ways that we can't necessarily predict. But I would say that the theoretical uncertainties on how one does fragmentation, there's no proof of Cooper-Frye. So, I would say that this will always add maybe even more uncertainty.
So why Cooper-Frye? Why not just fragmentation?
Well, I am just. Of course, fragmentation for this, but I agree. But my point is more generally that when anyone is trying to include fragmentation, there's a lot of uncertainty. So at least what I'm seeing here, I can be sure that it's just about gluons, and I at least understand, or I try to understand where things are coming from.
Right. But I mean, the bigger picture is, of course, the two-point correlation function. Taken at face value is not an inference safe observable, right? Therefore, of course, it is sensitive to fragmentation function effects. And in a way, Larry is right. We have to look at observables which are either insensitive to fragmentation or we have to include fragmentation conventions.
Well, what about multiplicity being fragmentation?
So I mean, jet people have all this infrared sensitive observables like thrust, right? And then about the name. There are other observables. Those are insensitive. Everything else is sensitive.
Multiplicity. But I mean, multiplicity being like 0 to 5% centrality is specifically sensitive to any fluctuation you try to use, including fragmentation.
Okay, so.
No, I'm not saying that. I'm not saying
one should do better than
one should do better, but we are unable because it's too hard.
Convolute the distribution.
No, what about the fluctuations? I mean,
two-point correlation function. You just put two fragmentation functions in it.
Now multiplicity being. So think about this process fragmentation. It's not an average. I mean, when you do this convolution, this fragmentation function, you assume that it's an average.
The factorization for the inclusive other aspect.
We need
not event by event.
We need event by event to do this 0 to 5% binning.
I believe collinear singularities factorize event by event too, I guess.
I mean, the fragmentation function is defined. The definition gives an average number of hadrons.
It's a single inclusive.
A single inclusive quantity.
We could generalize it to double inclusive.
No, we need again multiplicity bias.
So what fluctuates?
Well, for example, for what he's talking about is to do PP at the LHC, right? That's a example they have in picture. The proton to pion ratio changes by a factor of 5. If we go more higher multiplicity PP events versus average PP events, it's really a huge difference. So obviously, fragmentation, just from putting it in multiplicity bins, fragmentation is completely different for.
So you have to use
you're biasing yourself towards.
You have to use subject Monte Carlo or something, right? Monte Carlo for fragmentation. And that's what it's
Yeah,
that's kind of the point.
Well, I mean, you don't need to do that. I'm sure you can do it natively and
Yeah, okay. I don't
save yourself.
You know how to do the multiplication.
what is done and you think,
Yeah, how do you done? The multiplicity is no longer numerical, right? Because you don't need
okay.
Okay.
This card.
Yeah. Okay. Yeah. So this is good. But so where are these correlations in this framework actually coming from? It's sort of and I guess I think I'll label it as a guess that we sort of put forward is that okay. So what I showed you was the 0 to 5 multiplicity class, which actually is changing the average multiplicity for the 3 systems. So for proton, the average multiplicity is going to be smaller than deuteron or helium-3. So you're really, when you're looking at this fixed 0 to 5% multiplicity class, you're looking at larger average end charge for the larger systems, and then this is sort of giving you a larger, at least parametrically, QS of the projectile times S perp, so that the transverse of the overlap area. And this just comes from dilute-dense sort of scaling relation that's well known. And one could then suggest that maybe it's this.
Don't worry, this is somebody joining the meeting on Zoom. So this is not the police after it.
Okay, and so maybe this larger average end charge will then give a larger QS of the projectile times this perp, and so depending on how these configurations are, this then generates sort of larger correlations, or at least could maybe explain why we see this ordering where proton is less than deuteron, which is very close to helium-3. If this interpretation, or if this sort of naive guess on why the correlations are being generated is correct, then the natural consequence of this would be that same multiplicities, if you look at the same, for 2 different systems, if you're looking at the same multiplicity class, then the correlation should at least be similar. That it's really sort of similar QS squared S perp for between the 2 systems, and that's really then what's going to give you your correlations. Just want to say though, this is really a nonlinear system, and so there are also quantum effects which come by taking into account these rows that I introduced previously, and so classical intuitions may be somewhat misleading. To try to sort of piece this apart, and I don't want to spend too much time on this figure, even though I know it's very busy, but just to say that I can look at sort of what the average distance between the 2 nucleons are in the deuteron, which I call this DNP, but what's sort of maybe a more correct thing to look at would be this distance minus twice their sort of the RMS radius of this sort of Gluon cloud, in a sense, that one assumes. And so, of course, this is somewhat of an assumption that you just have, that your nucleon is really a Gaussian distribution of color charge with some characteristic width that is fixed by fixed Tahara data, but going with this at least, that we can see so here I'm binning both as a function of the separation of sort of like their tails separation, what I call d-sep here. So I bin as a function of this, and then also as a function of multiplicity, and as a function of the value of V2 at 1 GeV, just for simplicity. And I understand that this is very busy. The only thing I really wish to draw your attention to is that despite that there are many sources of fluctuations, including projectile, target, QS fluctuations, color charge fluctuations, that we see that very close configuration. So this d-separation of 0 seems to be sort of something that gives a lot of events, and maybe this would suggest that high multiplicity events sort of bias toward, especially here for the highest multiplicity class, I consider that really these high multiplicity events are biased towards overlapping deuteron or nuclei and the deuteron.
If you look at the vertical axis, it seems that low multiplicity events seem to have a higher V2.
Also, low multiplicity events, you still have the maximum and negative.
You still have I mean, of course, yes, there
on
is.
the left, why the maximum is still for negative d-sep?
So yeah, this is the maximum, or like sort of where you have the most events. I mean, of course, this includes all of this data. So seeing this very
where
bright.
is the 1 Fermi separation?
Sorry, the 1 Fermi separation. So
of the neutron, the proton is linear bias.
I'm confused.
I thought that minimum bias events,
Mm-hmm.
the neutron and the proton are separated by about 1 Fermi. That's
No,
what I
why,
was told
but
by-
of course,
looking at this solution.
but
Because they subtracted the values of the distribution of the proton, maybe.
But you're talking about the average.
Yeah,
This is the-
yeah. So here,
the distribution.
yeah. So
It's not completely linear, like,
no. So here, what I'm doing is this. This is where I'm imposing no cut on multiplicity. So this, and just looking at what are the distribution of this separation of the two nucleons.
so they're never separated.
No, they can. I mean, of course,
Maybe
there's.
it's a question of variable, because
Yeah.
he uses as a variable this separation is the difference between the center of the two neutrons minus the two square root meet.
Yes.
So he
Yes.
Exactly. It's only one family
Ah.
part.
minus
Oh,
one is
maybe I
over.
misunderstood your question. Yes. So I mean, even like when this value is something like -1, then there's a full overlap, which would really actually be that they're sort of collinear going into.
So then it's going to higher multiplicity. It does not change this.
Yes.
It's
Well,
always
you
the
see
same.
that it's a little bit more, I would say, peaked at this small separation, maybe. I mean, of course, so the one point I would actually like to make though is that there's many sources of fluctuations in all of this. So to actually discern which configurations are driving, are driving V2 versus the multiplicity is somewhat hard to disentangle because we have fluctuations in the position and impact parameter for both the nucleus or for the projectile and target nucleus. So, and that's why that I would say.
I just have one other question about
Sure.
that. So it looks, if I understand your normalization right, it looks like in the higher multiplicities you have a relatively smaller probability to get a high V2. Am I reading that correctly? I thought it would be the other way around.
You're saying that you would expect, that this. I mean,
So the upper left corner has got is emptier in the higher multiplicity.
Yes. Yeah, I mean, but this plot I admit is a little deceptive on how to to actually if you sort of so now there is not much change in V2 say between the 20 to 30 and the 30 to 60, and then it's sort of flat, really. But and so it just then sees you're sort of seeing how this distribution shifts. And at least the conclusion that I'd sort of like to put forward is just that this sort of shifts a little bit more towards closer configurations. But it's very weak. I'll show this again, but in a little different way, and maybe it'll be clear. Okay, but so then just very briefly, I'll say that instead of looking at this very complicated fluctuating picture, instead I just take a deuteron and I then couple it with a target in the MV model. So this is really just an infinite sheet of color charge, right? So then I no longer have impact parameter fluctuations. I no longer have any sort of target position fluctuations. And so the separation in the deuteron is given then in terms of the wave function. And so actually the position and the separation between the proton and neutron is given by this, which is roughly, I think, a gamma function or something. Or a gamma distribution, excuse me. But the point that I'd like to draw your attention to is that for very small separation, that the scales are parametrically like d to the 1/2, and so this would say that it's somewhat unlikely to get a very close close separation.
Right, it would probably be more useful to plot what this is for the just projected to the transverse plane. Or this is transverse.
Yeah, this is projecting to the, so this is why, so I'm taking this radial distribution and sampling my two nuclei, and then I'm looking at what they are when they're projected onto the transverse plane, just the distribution of distances. And just to say that, it sort of becomes highly, this is really having these very closely separated proton and neutron in the deuteron, it becomes difficult. However, then if I look at a sort of a very pedagogical example, which would be, then I calculate the multiplicity distribution where I fix, again with this MV target, but where I fix the position of the two nucleons in the projectile. So one I have where they're overlapping, and another I have them where they're very far separated. And so you can see that really there's sort of sort of exponentially biased to, so if I have this very close proton and neutron in my deuteron, that I'm really able to generate a lot more high multiplicity events. So even though the separation is suppressed, these are the configurations that really make a lot of high multiplicity events. And then I just show this again in sort of a nicer, more compact way, just to say that, at least for this nice clean MV model, which I'm using really is just a test case, that you can see that there's really a smooth dependence on this deuteron separation and the given n charge for a given average separation D. Here this is normalized by the total average Gluon density. But so there's really, as I get to closer and closer configurations, I can start making higher and higher multiplicity events. And so then this would at least suggest parametrically that I have a smallest perk, but I would then need to increase QS when we get to these very close high multiplicity events. And so that in high multiplicity events where close configurations are biased, that this may.
Can you discriminate between these different scenarios with HPT? Look at high multiplicity events and look at HPT.
I don't know, Vladdy, can we? I mean, so at least for deuteron, I mean, there's some talk about trying to do some sort of engineering of the. If you look at a deuteron with spin, you can then at least look at, I think, the sort of there's some correlation between the alignment of the deuteron.
Well, but HPT is pretty direct, right? You have lots of particles in these events, so I mean, you might think it would be kind of a natural thing to look at. And you're saying you don't have any other way of getting it. So
yeah, so I mean, this would certainly be, in all this discussion that's been ongoing about if these correlations are CGC versus, or CGC dominated or hydro dominated, I think having a way to actually discern what the deuteron configurations.
You're saying the size scales are quite different.
Yeah, so I mean, this would be something that I think would be very interesting, but how to actually access what this configuration looks like. I don't know if one can do this with HPT.
Well, HPT, you look at the transfer size.
Yeah. Okay, I'll have to look more into this then.
I think people are analyzing the HPT for those deuteron and helium-3, I'm not sure.
Okay, well, that would be very interesting then. I mean, certainly would give us some sort of constraints on what we could expect.
But you don't have spatial information.
I mean, it does. This is,
Where does Gluon come from?
no, but this is good. I mean, but the spatial information about whether the two
Yeah,
metrics are overlapping or not is
particles
crucial.
in the end, right? And you have to know their position, and you have to put in a wave function so you can interfere and all this, right? You want to do an HPT calculation.
No, I don't think the point is calculating it. It's more.
Measure.
I don't think you can calculate HPT.
Yeah, I can, but it's what is told to us
Because-
from people doing the HPT.
Because here this is
Yeah.
very clear.
You would want to know what to expect, and I'm not sure that you actually.
Well, I mean
on
just
average.
generically for the computer, what he's saying is that high multiplicity events are really overlapping.
Yeah, but
So this would mean that the generic prediction from here would be that high multiplicity events have small HPT radius.
right? So you have two sources now, independent sources. You have these two blocks. And the interference is what you really want, right? So one would really want a calculation of what you would actually expect. Right? I mean, it's not just one source in the case where they separated, but two sources. You have things on one or the other
What is
interfere.
the expected HPT signal from two completely uncorrelated?
Right.
Gluon?
No, but this is always the case. You want them uncorrelated, right?
Yeah, I mean, of course, they'll have some tails, right? That will.
Yeah, so I mean,
But
But still, I mean, how is that different from the HPT signal from a nucleus-nucleus collision? Where certainly there's somehow the different edges of the thing are of the overlap system are very uncorrelated. You still somehow want to extract information about the size of the system.
yeah, I guess that's true. That's what you have information about how far in the person can be applied.
But you might see a differences in the two transverse directions, right? If you just do a very garden variety, one-dimensional HPT is confusing, but maybe if you do the 3D and look at the outward versus sideward, it might.
Maybe. Although then that becomes entangled with somehow the ends, because then you're measuring outward sides and with respect to the momentum of the particle.
Yeah, but you can do the, as someone said, the event shape engineering, select on VN and then see if you can tell any difference at all.
Yeah. Yeah. So I think this is sort of along the lines. Yeah, I think this is somewhat along the lines of what we were thinking, in trying to understand, what is really, what are the characteristics of the correlations, or what one sees actually in the CGC picture, and then so what I showed before was the very smooth MV infinite sheet target, but then if I actually include all the fluctuations, again we can see this dependence with increasing multiplicity, this bias towards closer events. Now, of course, it's not as strong as what you saw for this infinite MV target, because you have fluctuations in the target. So it's not only just hitting an infinite sheet, but actually making contact with nucleons in the target. So of course, there's still sort of more to be understood, especially then with where V2 is coming from. And this is really, I would say, still work in progress. So trying to really understand what is driving V2, what types of configurations, but I think understanding all of this will be very important to try to distinguish between these two sort of scenarios, at least in their asymptotic limits. Okay, and then just last point I'll make is just going back to this conjecture that I sort of proposed when trying to give a naive explanation of our results, which is just to say that the similar multiplicities, at least in this type of picture, as we kind of understood it, should give somewhat similar correlations. And so this was actually measured recently by both Phoenix and Star, and I apologize for this extremely busy plot, but there's a point, which is that the Star data is shown here for 3 different methods, which I won't go into at all, but then superimposed on top of this is the Phoenix results, which also includes some theory calculations from Sonic Hydro and also our calculations. And it's just to say that currently, I would say that this conjecture, maybe one can't make a clear distinction of whether or not this really holds, especially given the sort of systematic uncertainties between the different, both the experimental collaborations and even internally their sort of methods that they're using to get these. But if one, say, focuses in on this Star template fit, you can see actually a fairly reasonable agreement between proton gold and deuteron gold when one is looking at the same multiplicity class. So at least I would call this intriguing, and I look forward to hopefully a lot more measurements on this by both collaborations at RHIC on this system size scan. So then,
let's see, in the proton gold collisions, right? Do you have a similar effect where there's a difference between the typical separation between the nucleons and the gold nucleus, which as a function of multiplicity, the question being in a hydro calculation, do they tend to be skewed out around the nucleon which goes through, or do they tend to pile up?
So this I don't actually know the answer to. I haven't looked
because
at
there
really,
they do have HPT data on this function.
So yeah, what the clustering looks like in the target around like that the proton strikes in different events. This I don't know.
Because I know early on the kind of hydro calculations had it more separated. But
yeah, this would be
maybe
interesting.
You can ask the question there,
well.
and you have data immediately which can answer.
Okay, so then I just sort of the highlights, which should just be that that in this dilute-dense CGC framework we can at least come up with some argument for the observed scaling and multiplicity at the LHC for V2, 3, and 4. We've also introduced a full event-by-event CGC dilute-dense CGC framework, which this was able to qualitatively describe the hierarchy in V2 and V3 seen at RHIC in their system size scan. Just want to sort of impress one more time just to say that color charge fluctuations in these quantum correlations are really key to this picture. and that one cannot just appeal to classical intuitions. It's much more complicated than that, fortunately. And really, to quantify though the roles of initial state versus hydro in these small systems, I really think that it's important to have access to more multiplicity distributions and also different measurements of anisotropies, to really be able to sort of push all of these different frameworks and see where they break and where they still do okay. So, all right. So with that, I say thanks.
Okay. Any other remaining questions? If not, let's thank the speakers, both speakers again.